I think we can move to the next presentation, and I have the pleasure to introduce Klaus Michael Lehr. Klaus Michael is professor at the Saarland University and is head of the Department Drug Delivery at the Helmholtz Institute for Pharmaceutical Research in Saarland. He's co-editor of the European Journal of Pharmaceutics and Biopharmaceutics and has been the initiator of the International Conference and Workshop Biological Barrier. By the way, this year, the conference will be held in September 7 and 8, and it will be only in the virtual format. The abstract submission is still welcome. In 2019, the British magazine The Medicine Maker rated him for the third time as one of the top 100 scientists most influencing research in the area of drug delivery. Please, Klaus Michael, the floor is yours.
Yeah, many thanks, Laura. And I try to share the screen. Okay. See how this goes.
And Klaus, I will tell you 5 minutes before.
Yes, that's fine. So just I'm in the at the. So somehow the
you have to share your screen on the right. Yes, you're close to it.
I know you should. Do you see it now?
We exactly.
Yeah, and you see it in full screen mode?
Yeah, perfect.
Then it's perfect. So now I can start. Yeah, thanks a lot. I go right into this. So my name has been explained, my affiliation has been explained, and also since more than 10 years now, actually, I'm also leading such a department of drug delivery. We call it, in fact, Biological Barriers and Drug Delivery at the Helmholtz Institute for Pharmaceutical Research. So my field really is actually drug delivery and pharmaceutics, and I like always to show this to this illustration that we, in fact, in my research, we are dealing with two things. We are dealing with carriers. Some people also call it formulations. Formulation may be appropriate at the macroscopic scale. When we talk about the nanoscale, carriers may be more appropriate to refer to actually overcome biological barriers, to get drugs to their site of action, because there's always something in between the site of action and the site of application. And for that, you need a certain technology. Well, making these technologies is one thing that involves engineering part and processes. On the other side, designing systems also requires to understand the biology or the nature of these biological barriers. You need to develop different carriers if you want to overcome the skin or the intestinal mucosa or the lungs, which is the topic of today and which is one of our favorite topics. And over the years, we also moved into non-cellular bacterial barriers like biofilms and the bacterial cell wall itself. And in that context, I found it in the beginning of my career extremely useful to look at these barriers, to make models of these barriers, to better understand and to design the delivery systems that I actually want to make in order to overcome these barriers, and that you then have an alternative to animal testing and that you work with human systems is actually a big advantage that hopefully, and this is my long-term hypothesis, that these models will facilitate eventually the translation of new drug products into the clinic, because we want to predict what happens in humans and not what is relevant to an animal. Having said that, here my 5 little appetizers that I try to bring through in the next 25 minutes. And I will start with some concepts, actually nicely starting there where Ottmar had ended. The aerosol technology, I'm not saying we can take it for granted, but meanwhile, if we want and have the right technologies, we can go into the lungs, we can go into the deep lungs. And this was also by John Patton, by the way, the inventor of the inhaling insulin, a photo that had inspired me as a young postdoc very much that I should go for the lungs. It's a tennis square, large surface area. The towel is just the airway. And in addition to that, and that's another one of my big inspirators, Peter Gehr, who showed this this photo at a conference and I got caught by the fact that this barrier is not extremely large. It is also extremely thin, less than 1 micron, consisting of an extremely tight layer of ultra thin cells. So great opportunities for doing this. But, you know, if you want to study the processes, you have to have a right model to do that. And when you walk along or fly along the respiratory tract, you will realize that the morphology as the function of the epithelium changes. This is the towel area, the airways, we have bronchial, we have ciliated cells, we're going deeper into the lung. And finally, when we're at the big tennis court, we have this ultra thin alveolar epithelium composed of type 1 cells, type 2 cells, and macrophages. This is a very simple system, here cartooned again by John Patton years back. And the only thing when we started, what was there was a cell line called A549, allegedly a type 2 cell line, immortalized and poor enough, if you're interested in transport, very low transepithelial resistance. You can see here the stained tight junctions. There are lots of leaks between the cells. You can do a lot of interesting research regarding single cells and maybe regarding the transport of larger particles. But if you want to study the transport of small molecules, this is really not a very good model. So Katharina Albert was one of my first PhD students who succeeded then in collaboration with the colleagues from the US, thoracic surgeons here, and in our department actually to grow first time a primary culture of human alveolar epithelial cells. And that is quite nice. They look like type 1 cells. They have a resistance of more than 1,500 ohms, so that comes close. And that was 1999, so quite some time ago. We worked more than 10 years actually on attempts to immortalize these primary cells to come to a cell line. And finally, now this is also 5 years ago that we published that there is a cell line that you can use. You can buy it. It's called HELVI for human alveolar epithelial lentivirus immortalized cell line. So they used a set of mildly proliferating genes. And with that, we could maintain the type 1 characteristics and the high resistance, the true barrier properties, which are in context of drug delivery, the most important thing, and keep these cells available and alive over several passages. Well, we heard then also there were problems. In some labs, the cells worked fine, in others not so much. And then we realized what we had actually created was a polyclonal cell line because we had selected for EBCAM positive cells. And there are many, many cells who have these elements. So maybe you create every time that you thaw a vial with these cells a different type. And then we thought what we need to go to is actually a single cell clone. With this technology, you can select, it works like a little fax. You can select single cells and then grow these, in fact, and we picked the different cells and we took this one which grew best. And according to a custom that you give names by the alphabet, male fail names, our technician suggested the first one was actually very promising, and I think it is maybe Finnish in any event. His name is Arlo. Here I may introduce to you Arlo. Arlo is our super, I would almost say Frankenstein alveolar epithelial cells. They grow strictly as monolayers. They're a little bit more cuboidal than they should be for type 1-like. So I would not call them type 1 cells, but look at these resistance values. It's incredible. 4 kilo ohm per square centimeter that you are getting. So with this, you can really do interesting studies. This is an ongoing gene expression analysis where you see the tight junctional proteins are very highly regulated. We are currently, of course, everybody is doing COVID research, and we have been using Arlo also in some collaboration with colleagues in Frankfurt. You see that you get the replication of the virus in these cells. You see even the expression of TEMPRESS, this of the ACE2 receptor. You can even see that during the infection, the expression is increased. So it's really an exciting model because that is essential for that part of the lung, not where you catch the infection, but where you eventually get this RADS-like symptoms and possibly even die at the end. You see this here a little bit in a simulation. We grew and observed the resistance. This is how they grow normally. you say easily they get 1000 ohms. If you open the tight junction by brute force with EDTA, you have no resistance, but by the virus, it would say it's significantly reduced to about half of it. So that means you see what the virus is doing. And of course, this is a platform to, remarkably on human cells, can study protective agents and things like that. So that's maybe a useful contribution. So we move forward, and Ottmar has also alluded to that theme of air interface versus liquid interface, deposition, and I can only confirm the importance by quoting a paper that one of my students, Michael Boer, had published. He quite nicely put particles, I think it was salbutamol, on air interface conditions on the, so to speak, naked cells, and measured the transport to the basolateral side, and you see it goes very quick. When we added then stepwise a little bit volume to the apical volume, this is very similar to what Ottmar just had shown. You see then just the intrinsic diffusion across the barrier. But if you do want to consider the fact that aerosol particles do deposit on the cells in the lungs and not in some liquid lining fluid, unless you want to have water in the lungs, which you don't, then you should go for a liquid interface conditions. And that's what we had started up with a simple system that we called Paddock as a nickname. It was a little bit self-made, and you could already by that time connect a commercial handyhaler to, again, we are interested not in exposure to certain concentration of noxious gases or particles in the atmosphere or in a room. We want to simulate what happens if a patient on purpose takes a deep breath, and hopefully the complete dose goes into the cells. It's similar, but a little bit distinct scenario to these questions that are relevant to toxicology. Then also VitroCell, a company already nicely introduced, picked that idea up. We collaborated together, and this system is now actually commercially available as a VitroCell powder chamber, and you can use this for these purposes to make controlled deposition on cells. Well, organs on the chip, also this has been alluded to. You have these chips, and you can move from the transwell to more complicated things, to introduce cells and to introduce deposition patterns. We here teamed up with Josi Snitman's team. We met each other at an ISA meeting, immediately became friends, and there's a nice complementarity. And I don't want to give his talk here. He's going to speak later, but he has very nice, fascinating systems to simulate on a chip the airflow conditions before the landing happens. And our contribution was what I called then the software that could be put as cells into this kind of hardware. And another study that we are involved with is a European project with the company Alveolix and also VitroCell. They have commercialized and refined these breathing systems. So in fact, you can here, by applying negative or cyclic pressure, you can stretch the tissue, and has been known and nicely published already some years ago that this has effect on the metabolism and the activity of the cells. And we want to use it here to study inflammation. We have a co-culture of alveolar and cells and macrophages, and now we can actually do the breathing. We can stimulate an inflammation like it would happen if you apply viruses or if you would apply other pro-inflammatory agents. We typically do it with lipopolysaccharides or NF-alpha. And then we can see what is the therapeutic effect of potentially anti-inflammatory compounds and read this out. And as a drug development tool, because of its standardization and high throughput capacities, these systems certainly do have a value. For ourselves, we wanted to keep it a little bit simpler. We have next to the paddock something which we call the polypep. And this is a air deposition simple system for deposition, on air liquid interface grown epithelial cells. You can simply make it in every lab yourself. You can connect it with wires and tubes, then you can perfuse it, and you see transepithelial resistance, again, a very easy but strong biophysical parameter, shows that the barrier properties here on Calu-3 cells in these systems are actually the same like in others. We have here a little self-made deposition center. It worked by this stagnation point radial flow. Ottmar helped us, thankfully enough, a little bit to this. And also in order to improve that, the paper has recently been published, so that can really be looked up. All the details, if you wanted, you make it yourselves, are described. It's a on-purpose, non-commercial, easy to use, academically type of solution that can easily fit into a transfer system. So, and now we come to the hard stuff. What we want to see is actually a model of a patient like this guy here who could be suffering from mucoviscidosis, cystic fibrosis. And because of that, he develops an infection by Pseudomonas, and he has probably bacterial biofilms in his lung. And thanks to the good therapies, they can meanwhile survive up to 40 years and older. And if we want to mimic this situation, we do not need only epithelial cells. We also need not only drugs, but also we need bacterial systems forming biofilms on top of these cells and having this all in equilibrium that we can test aerosol administration of anti-infective drugs. All the different binary combinations have been described, but the challenge is to bring all these three things at the same time in such conditions. And this is what these three guys have done in the past few years. Now the first paper come out. That was still an easy thing, epithelium and endothelium together with macrophages. As long as you don't have bacteria, that works. Not too difficult. If you want to bring in bacteria, you will realize why typically people growing human cells try to keep the bacteria and fungi absolutely out of reach and out of the lab. If you now are so active and put bacteria on purpose in, you see that within hours the bacteria kill your cells and there is nothing left that you could use in any form as a model. Well, we saw some achievement, but this was really just a start and a learning process that this is really something that you need to do better. Well, we made progress. Here you see a co-culture with bacteria on top, with bronchial epithelial cells and macrophages on the bottom. They go through the epithelium, they pick up some of the bacteria and go back again. This goes already into the direction. But the real nice work around what recently developed by Justus Horstmann, he said, okay, if I want to study biofilms on these cells, I have to grow the cellular monolayer separately in one batch, while on the other cell, I grow the bacterial biofilm that I can see the conversion from planktonic state to biofilm state. And only after a couple of days, after a week, in fact, when both are mature, it comes to the marriage, you pipette and suspend and put the pre-grown biofilm back on these cells. And when you then have early conditions, you can then see, you can even do a repeated application up to three times for 27 hours and see what comes out here. Well, there's of course a lot of characterization to be done. This paper will hopefully soon be out. You have to verify that biofilms are on top of the films. You have to quantify them, that you see this is all under control. You also have to verify that you do have biofilms and not planktonic bacteria. You can measure this by checking the resistance against antibiotic. Biofilm bacteria are much more resistant, less susceptible than planktonic ones, and that you see here, we looked for some metabolomic similarity. And again, they show that in these Venn diagrams, the transferred biofilms have most similarity to native ones. We can consider them as largely biofilmic rather than planktonic. And here comes into the play the system that already had illustrated.
You are hard to stop where I find the moment where you're not talking. We are almost 5 minutes before the end.
Yeah.
Okay.
But I'm okay. You're talking to me, right?
Yes, I'm talking to you.
Good.
So you are 5 minutes to the end.
Okay, that's what that was. I had planned indeed.
Good,
so we can measure epithelial barrier integrity and inflammation of these systems, and we can measure, and this is the last bit that I wanted to tell, we can measure so-called quorum sensing molecules. Quorum sensing molecules are communication factors, And when we cut the communication between the bacteria, we can actually overcome bacterial resistance much more effectively, and we can eradicate Pseudomonas biofilms and not only reduce it. So this is the collaboration that I want to show as an illustration why we as pharmaceutical scientists are using these systems. We want to co-deliver an antibiotic and a quorum sensing inhibitor, these new type of non-antibiotic anti-infectives. And for that, we need nanocarriers that can co-deliver two compounds with rather different physicochemical properties. And with this nanocarriers recently described in that papers, we can do that. You see here, when we just give the antibiotic, even at the highest concentration, we cannot eradicate the biofilm. If we put these alone in a nanocarrier, it goes better. But what you need is the quorum sensing inhibitor, with which we can, and that is nice, double the activity, save half of the amount of the antibiotic. But when you do the two in the nanocarrier, as you can see here, you can actually enhance the efficacy 30 times. In other words, you need 30 times less of the antibiotic to not only kill some bacteria, but to eradicate the biofilm. And these are true perspectives for a complete cure, a complete eradication of such diseases. And as I hopefully could demonstrate, such in vitro models can play a very helpful role. Thanks to my team and our sponsors, a hint to our biobarriers. If you want to attend it, then I invite you indeed, look at the website, you just Google biological barriers, and there are still opportunities. We have already like 80 registrations and a bunch of nice and good speakers also on technology side where we can there. And still, I think I was within my 5 minutes. Now I'm done. Thanks you very much.
Thank you, Klaus. Thank you. And sorry about this.
Yes, Klaus, this was really a great talk as usual. We have several questions from the audience. So I don't know which one to select first, but let's start with one which is general concerning the influence of basal medium volume influencing also a drug diffusion. Would you advise to always put a volume reaching the level of the membrane or not higher? Or is it model dependent?
Yeah, actually depends on, let's say, you have this problem with hydrostatic influences. I would simply say, just keep them with the 2s in the water, just get them maximally wetted from the lower side. By the moment you make the outer medium higher, you have a hydrostatic pressure that increases the water to flow from basolateral upwards. So this situation you should avoid. And the other thing is, what you would like to see is just a humid, maximally humid environment and not a wet environment. Ottmar illustrated that the drug has to diffuse through the water first. And in addition to that, if you have any kind of drug carriers, also just lactose particles that come along with many aerosols, they exert physical effects on cells. That has been known on the nasal cells, and somewhere else you can dehydrate cells with spray dried sugars, open temporarily tight junctions. All these effects which can be exploited, you will be missing them if you work under underwater conditions. So just grow the cells, but as you want. But during the experiment, I would, if you want to study aerosols, always just keep it from the bottom.
Thank you. A second question, if we may. So could a fluidic system help overcome the fact that bacteria overgrowth kills the epithelial cells?
Absolutely. That's the reason why we have emerged. That was the motivation for us to come with this polyp system. The transfer system is fine, but the transfer system has no elimination. It has on the basolateral compartment, it will run up. This is when you study drug transport and you keep sink conditions, means from 100 to 0%, maximally 90-10, then it's no problem. But by the moment when you have bacteria that are releasing virulence factors, they will accumulate. And we thought it is important to perfuse the basolateral side with fresh medium in a single pass perfusion to actually remove these steps and to have an element of elimination, which from pharmacokinetic point you do not have in the standard transwells. And that was a simple realization. There are also several other commercial systems, but we tried them and they did not work. And then it was the easiest to come up with the system for ourselves.
Thank you. Another questions from the audience. Could a fluidic system help overcome the, no, sorry, what, sorry.
That one we have.
Because, sorry, everything changed. Yeah, yeah, have there been successful submission of new drug application using some of this system?
Not formally yet, because, you know, this is the what comes first, hen or egg thing. For the moment, we don't have any approved and validated system that we could use as alternative to animal testing, like you have it in other fields of, yeah, like pyrogenicity or many skin models are there. That was because of the ban of animal experiments in the cosmetic industry. There was an enforcement to work on these systems. We don't have such a ban in the pharmaceutical field, just companies are realizing that they're making advantage, that it works faster and the failure rate is less. So with this progress of such systems being used more and more, the amount of data will increase. At institutions like ECWAM, you will see that there will be applications for validation of these models. And once we have the models validated, then of course we can use them. For the moment, I can only tell my industry collaborators and partners, we will definitely learn something by using these systems, but for the moment, we cannot use it yet for proving anything. So you will, but you can use your most robust system, your drug delivery system that turned out to works best in these in vitro systems. And then the chances that you will successful in preclinical and later clinical studies are simply better than if you, let's say, don't know anything about this. It will come with time. That's my answer. Validation is important.
Great, thank you. Another question which is really related, and to some extent you have already answered, but concerning regulatory agency, do they recommend specific cell line or models to develop in vitro assays?
Well, it's a kind of a back and forth game. If you are kind of beginner with these systems, then the easiest if you can buy cell lines or even pre-grown systems like yeah, some companies organizing such fantastic conferences are offering. That is probably your first thing. If you want to do more sophisticated things, you want probably also to see primary cells, but then later on for the standardization and validation, you will need to come back to something which is reproducible. And then you probably have to make a compromise. How was this Albert Einstein thing, speech or quote? A model must be simple, but not simpler than necessary. You know, you need a certain level of complexity that you, depending on your scientific questions, things are too complicated, you lose the clear view, you are in a black box situation. That is the problem of all the animal experiments. Besides the ethic aspects, you don't see what is happening inside the lung. Well, we have seen the nice pictures by Ottmar, but still is essentially something you cannot look into and not at the cellular scale. Taking the complexity of the processes out, the processes of the transport out of the complexity of an animal, that is the beautiful tool that we can do. And when we then work with human cells, we have all aims to manipulate parameters, pathophysiological ones, to put it under the microscope. We will understand better what we are doing also in vivo. It's a concert.
Thank you so much, Klaus Michael. I think that for a sake of time, we should close now this first part of the sessions and have a break. So we have a break until 10:30, and we will continue again with this morning sessions with Laura Glebaldo at 10:30. So please take this opportunity with this break to have a look on the Share Your Science, where posters are available on let's say the Epithelix website. You have the link here. Just please feel free to visit this gallery. Thank you so much for the speaker for excellent talk this morning again, and see you at 10:30.
Good.